Hi guys, I am Yashodhan Agnihotri, a final year student at IIIT Pune, and I will be your host for today. Welcome to our channel, Learn Competitive Programming with CodeChef. On this channel, we post weekly problem explanations and concept videos. Also, if you're interested in data structures and algorithms and wish to pursue and learn competitive programming, then this is the place for you. If you haven't hit the subscribe button yet, please do and click on the bell icon. So the problem in discussion today is from the recent November Lunchtime, and the problem name is circle coloring. The difficulty level of this problem is medium hard, and the prerequisites are dynamic programming and square root decomposition. So let us see the agenda for today. First, we will try to understand the problem statement. Next, I will take you through the detailed solution approach. Lastly, we will see the pseudocode followed by the C++ implementation walkthrough. So now let us try to understand the problem statement. We are given n sets of integers a1, a2 up to an. For each valid I, let us denote the elements of the set by ci1, i2 up to n. So basically we have been given suppose a number n at the beginning, so 4, and then we have 4 sets of integers. Let us denote them by something like this. This is the first set. This is the second set, third set, and the fourth set. Okay, so now what we have to do, we have to find the number of ways to choose a sequence a1, a2 up to an such that each ai belongs to one set. So one element from this set, one element from this set, and such a sequence. So basically let us take 1, say 2, 3, and no, so 1, 2, 2, and 1. Yeah, so this is a sequence. But now there is another condition, that ai not equal to ai plus 1. So consecutive elements cannot be equal. And also a1 not equal to an, that is the first and the last element also cannot be equal. So you can term it as a cyclic array where each consecutive element should not be equal. So this 1, 2, 2, 1, it's not a valid sequence. So a valid sequence, instead it would be that we take 4 from this, we take 3 from this, we take 2 from this, and we take 1 from this. So this is a valid sequence. Now we need to find all such valid sequences. Okay, so let us take a look at the constraints. These are the constraints of n. It is between 2 and 200,000. These are the constraints of the number of elements in each set. So the number of elements in each set will always be greater than 1. And this is another important constraint, that the sum of the elements will not exceed 200,000. So sorry, the sum of the elements, like the sum of the number of elements in each set, it will not exceed 200,000. And each element in the set, it is between 1 and n. So let us move on to the solution approach. Before we see the solution, let me explain you the sample case. So here we have been given the number of sets as 3. The number of elements in first set, that is 3, are 1, 2, and 3. The number of elements in the second set is 2, and they are 1 and 2. And the number of elements in the third set is also 2, and the elements are 2 and 3. So let us try to make sequences satisfying the conditions that ai should not be equal to ai plus 1, and a1 should not be equal to an. So basically in a cyclic array, the consecutive element should not be equal. So let us make our first sequence. Let us take element 1 from this, let us take element 2 from the second one, and 3 from the third one. So this is a valid sequence. Let's try to make one more sequence, taking 2 from the first set, 1 from the second set, and 3 from the third set. This is again a valid sequence. And another valid sequence would be, I think, 3 from the first set, 1 from the second set, and 2 from the third set. So if you see, there aren't any more valid sequences. So the answer for this case is 3. Also, did you know that CodeChef also conducts free live classes on Unacademy where we teach every possible topic related to competitive programming? We have beginner level courses like Introduction to Programming in C++ or Java, Recursion, Basic Data Structures, or advanced level courses like Graph Theory, Dynamic Programming, and Segment Trees. These courses are conducted by top coding experts who have been ICPC World Finalists, IOI medalists, and work in top product based companies like Google, Amazon, Facebook, and LinkedIn. All you need to do is download the Unacademy app and choose your goal as competitive programming. You can also take the paid plus subscription to get additional features and individual level support. In plus, we have a large set of practice problems associated with every topic covered. Also, we have 6-star and 7-star teaching assistants to help clear your doubts during and after the live sessions. You can use my referral code, which is ZAP10, to subscribe for the plus classes and get an instant 10% off. So hurry up and don't miss out on this amazing opportunity and kickstart your journey towards competitive programming. Let us now see the approach to the solution. First, let us solve this same problem for a line sequence and not a cyclic sequence. That is, we have been given the condition that a1 not equal to an. This should hold. So now let us, for the time being, let us ignore this. So we can say that the total number of elements, let them be m. So now we can state that a1 plus a2 up to an is equal to m. Now we can say that a choice for an is only dependent on an minus 1, because if we know the value of an minus 1, then we know how many choices we have for an. So let us draw something like this and kind of try to derive a recurrence relation for this between the n minus 1th and nth terms. So over here, let us introduce a term, that is answer n minus 1 comma x. So this term, it represents the number of ways to solve for the first n minus 1 elements. So this represents the first n minus 1 elements. So the number of ways to solve for first n minus 1 elements with a of n minus 1 equal to a of n minus 1 comma x. So this is the significance of this term answer. Now, as we saw, the relation between the n minus 1th and nth terms, therefore the recurrence relation can be written something like this, that answer for n comma x is equal to summation of y equal to 1 to a of n minus 1 answer of n minus 1 comma y. So if you see, this is kind of self-explanatory. We derived it from above. Therefore, the answer for line sequence, the total answer will be answer so the answer for the line sequence will be summation of x equal to 1 to an answer of n comma x. This will be the answer for the line sequence. Now let us try to analyze what will be the complexity of this. So let us say we have Si, that is the size of any particular set Ai. So the size of Ai is Si. So if you check over here, we have calculated, we have been computing S1 S2 plus S2 S3, and we are iterating the sets. So up to Sn minus 1 to Sn. If you check, this is equivalent to O of m square. So what we have learned so far from all the ways of choosing elements from the previous I-1 sets, we are removing the number of ways that chooses x as an element in set I-1. So I will show you later in the implementation part that the OM square, it can be optimized to an OM DP approach, and I will discuss it in the implementation. So let L be the answer when the sets are in a line, that is we are not considering cyclic array. So let L be the answer. So L is equal to summation of answer of n comma x. Now let us try to extend this to a circular, that is a cyclic array. So here we again encounter the condition that A1 should not be equal to AN. Now we must somehow try to achieve this. What we can do is that we can remove all those sets that we have included in this answer where A1 is equal to AN. Now let us see how we can achieve that. Now let us denote I as the intersection of the first and the last set. So let me write I is equal, so I is the intersection of the first and the last set. Now to fix the value of L, we saw the value of L which was mentioned above, that is the answer for the sets in a line. So we can just subtract all occurrences of all possible sequences with first and last element equal. So sequences like this, x, a2, a3 and up to n-1 and again x. So do you see over here that the first and the last element are equal, that is a1 is equal to an, that is both of these elements, that is x belongs to I, because I is the intersection of the first and the last set. So if x belongs to I, we need to subtract all occurrences of x. So we can do this how we did it previously by running the previous DP. But the problem is that I can be large, like it can be really large, because we can just get n/2 and n/2 for the first and last set, and then the time complexity will go really high. So the time complexity for this can go something like this into n. So this is really not desirable. So let us see how we can tackle this. So now let us try and analyze the bounds for I. So we can say that if n is greater than under root m, okay, then there exists a pair of adjacent sets, that is we'll denote them by ai and a of I-1, I plus 1, with a size at most m, at most under root m, and therefore for this case we can easily solve it in a time complexity of m root m. So the division into root m sizes of the set, it helps us because we are able to split the cases. So this is case 1 where n is greater than equal to root m. Now next we will see the case where n less than equal to root m, and that is a bit complicated than this case mentioned over here. So let us go to the second case. The second case is n less than equal to under root m. So we can also say that the number of sets is at most root m. Okay. So now let us try to build a recurrence relation in accordance with this condition. So we have C of A1, A2 up to AN. So this is our answer. Now here C is representing cyclic. So this is our answer, and all the conditions hold, where AI not equal to AI plus 1 and also A1 not equal to AN. So all these conditions hold. Now let L of A1, A2 up to AN be the answer for the line set, that is a straight line, that is we haven't considered this condition. So this condition does not hold true in this set. Now we need to subtract, so we need to remove some sequences from this to get our original answer. So through observation, we can get the recurrence that C of A1, A2 to AN is equal to L of up to AN minus we can say C of A1 intersection A2 comma up to AN. Now what does this recurrence tell us? We are, in every step of this recurrence, we are merging two sets, two adjacent sets, suppose AI and AI plus 1. So we are merging both of these, and we are forcing the recurrence to choose an element from their intersection, so that this particular sequence is not valid, and therefore we are subtracting this from L. So this is a very powerful recurrence, and it holds over here. This needs to be noted. Now let us analyze the time complexity of this algorithm. So here the in each merge operation, one set is decreasing every time. So we can say that this algorithm runs n times, and as we saw that this is the case too, and n is less than equal to under root m. Therefore we can say that the time complexity of this is again m root of m. Now we will see how this recurrence came into being. So I will give you a short proof, not the exact proof, but I will show you why this recurrence holds. So let us try to get an insight as to why this recurrence relation came to being, and how is it true. So we had discussed earlier that from the line answer, we need to subtract the cases where A1 was equal to AN, and those cases we needed to subtract to get our original answer. So now let us analyze the term C of A1, A2 to AN. Now how does this term work efficiently? So here what we are essentially doing, we are merging set A1 and A2, and we are merging set A1 and A2 and finding their intersections. So basically for this, in the place of both of these sets, we are replacing it with their intersection set, and we are choosing some element x1, let's say it x12. We are choosing some element x12 to replace this, so that we always violate the conditions, and we exactly are subtracting those sets that violate the conditions, which were AI not equal to AI plus 1 and A1 not equal to AN. So essentially this is what this function is doing. So let us see the pseudocode for this problem. We saw that the problem for a non-cyclic sequence, which is a line sequence, so this problem is solvable in an O of M dp. So that will be discussed in the implementation. Secondly, for case where n is less than equal to square root of m, we can simply count ways by replacing adjacent sets with their intersections, as we saw in the recurrence relation, that the circle is equal to line minus this intersection relation. For the next case, which is n greater than square root of m, there exists a pair of adjacent sets with intersection of size or at most square root of. So we have to break the cyclic array at that very point, and then after that we will solve it as a line sequence. And as we saw here, it is solvable in O of M dp. So this is a function that we are going to use again and again. So now let us go to the C++ implementation. Okay, so now let us do a quick walkthrough of the C++ implementation of this problem. So here I've defined a couple of necessary things. Here I've taken the mod to be what they've given, and here uh, I've written the add operation in the modulo. So this is the modular arithmetic add operation. Now the calc function. In the calc function, I have actually calculated the DP that I've been mentioning in the question, the OMDP. So here you can see I've calculated the OMDP. So here initially I've pushed back from the first set itself. I've pushed back into a vars vector num comma 1 pair, and then hence used it afterwards. Here I've used linear search to modify the pos and then add the current to the mod minus vars of pos dot second. So if you see in this calc array, I have overall done the DP. So you're free to check it yourself. Now going over to the intersection function, here I've taken input two vectors a and b. Now here I have another vector which is ret. Now this ret is my return vector. Okay, so what I've done over here is I've erased the set intersection of a dot begin, a dot end, b dot begin, b dot end from this ret. So this is basically what we saw in recurrence relation. That was a C of a1, a2, an and L of a1, a2, an minus C of a1 intersection a2, the set recurrence. Okay, so this is for the implementation of that. Now coming over to the main function, here I've basically taken the inputs, and here I have sorted all the sets accordingly. Now here I've written a variable int q equal to 400. Now why have I done this? If you remember, we are comparing n to the square root of m. Now what was the maximum possible value of m? So if you remember, the maximum possible value of m was 200,000. So as so the 400 is the closest square root to 200,000. It can also be something like 440 or 450. It won't matter. So here, if n less than equal to q, that is, I've taken the second condition first, and here as we see, we have the intersection of array 0 dot array dot back. So here we are calculating the second term, and we are outputting it as our answer. And here as we saw that the O of m into root m calculation of this, that where n was greater than square root of m. So this term, so for this case we are calculating in this else statement, and we are again outputting the answer. Now let us try to submit this code, and let us hope for a quick AC. There, we got an AC. I hope you have understood the problem. Thank you.